Hi, good morning. This is Trina here to discuss about entropy and how the process is the system is spontaneous or not, how it depends on the entropy and also the Gibbs free energy. So this is the fourth lecture of the thermodynamics, and already I have covered the 3 lectures. So I hope that you have already gone through the study material. So here I have given the course page where I have uploaded inter-study materials along with the questions and the solved problems. So I hope that you have gone through inter-study material. Still, if you not done yet, so do that immediately. First of all, you have to join with the given code, that is DMBC. Then you can access the inter-study material. And here in my personal information, I have given my email ID and the mobile number. So if you have any doubt regarding my lecture, you can communicate with me. So the subject chemistry and the subject code is CH101 for odd semester and CH201 for even semester. This course is for BTech undergraduate students and the streams are CSE IT Civil Mechanical for even semester and Electrical ECE BME for odd semester. The credits are 3, contact hours 36, and weekly I take the 3 lectures. Here, to understand the concept of thermodynamics, the prerequisite knowledge required, that is the 12th standard. And you will learn the course objective. What is the objective of this course? The students will learn the different concepts of chemistry. Like say polymer concept, like thermodynamic concept or organic reaction concept. So there are different concepts. So in the outcome for thermodynamics, the students will be able to apply the concept of thermodynamics in different engineering application. Okay, so it is the dynamics of heat energy. So it is very important for all engineering field. So students can apply the concept of thermodynamics in all the engineering process. Here the entire lecture plan given. So here students come to know that which topics will be covered in which day. So today our topic, it is the module 2, use of energy, use of free energy in chemical equilibrium. Use of free energy in chemical equilibrium. So here already the 3 lectures covered, it is the 4th lecture. So first I have told that basic concepts of thermodynamics. Okay, first one, that is the basic concepts of thermodynamics. What you have learned? You have learned different systems like say open system, closed system and the isolated system. And in the process, you have learned different process like say isothermal process, isobaric process, adiabatic process, isochoric process, etc. And the macroscopic properties, you have learned the 2 part, that is the intensive property and extensive property. Then you have learned the first law of thermodynamics and enthalpy. As per first law of thermodynamics, that is no energy or mass can be created or can be destroyed. So we can equate like say the Q is equal to W plus E, or you can represent the internal energy by U, either U or E plus the work done W. Okay, and you have also got the enthalpy. You can calculate the heat energy for the entire process, that is the enthalpy. You have learned to solve the problem with the enthalpy, and you can represent the enthalpy in terms of the internal energy. And in the third lecture, you have learned the second law of thermodynamics. It can be defined in a different way. So we have learned the Clausius definition. And also you have got the term, that is the entropy. You are introduced with the entropy. Entropy, that is the name of the randomness. Okay, so when the randomness increases, randomness of a system increases, then entropy increases. When the randomness decreases, then it will decrease. And today you will learn the estimation of entropy and free energy. And also you will learn to solve the problem. You can calculate the entropy for system and surrounding and the total entropy. And also you can tell that which process is spontaneous and which are non-spontaneous, or which are in equilibrium with the help of Gibbs free energy. So first of all, I like to show you one video that is related to the total thermodynamics. It is like you can see the first law of thermodynamics and the entropy, all these things. So here the different changes are taking place. Somewhere you can see the material is breaking, and somewhere it is formed and newly formed. So, but nothing can be destroyed and nothing can be created. So from there, the first law of thermodynamics we get is the energy can never be created or destroyed. The amount of energy in the universe is always similar. All suns and stars have a limited amount of energy. As a star emits light in all directions, it uses up this energy. So you can see the different phenomena. So it is the changing process. So energy can be thought as a boxes that are attached to all objects and can be transferred. These boxes can never be created or destroyed. That means E stands for, the boxes of E, you can see this stands for energy. So energy can never be created or destroyed. So here you can see the faster object have more energy than the slower object. Energy can hide in many forms. For example, spring has the potential to move objects. So our internal energy is the sum of the kinetic energy and the potential energy. So gravity also has the potential to move object. You know that object comes down by the gravitational force. So object at higher elevation have more energy because it has more potential energy. And the objects at the low elevation, it has the lower energy. Objects at higher elevation create more motion than when they fall. So you can see all these things, okay? And now you will see the entropy. Here the second law of thermodynamics states the entropy of universe can only go up. the entropy of the universe can never go down. So here you can see that how the balls are coming. Although there are many ways of balls can be arranged inside just one sphere, there are far more ways the ball can be arranged with the ball spread out between both spheres. So the second law of thermodynamics also we can represent in different way. The more evenly the balls are spread out between the two spheres, the higher the entropy. Now what you can see in the picture, this is why we will arrive at this situation if we wait long enough. Okay, so this is the randomness, and the randomness means the entropy. So randomness of the material, randomness of the molecules, that is called entropy. If it increases, randomness increases, that means entropy will be increased. If the randomness decreased, then entropy will be decreased. So here you can see that this would mean that entropy has decreased. Okay, so here you can see the movement of the balls. So in this way, we understand what is the first law, what is the second law, and what is the entropy. Okay, you can see it is the push all the balls back together again. There was only way all the energy could be contained inside the spring. Okay, so you have learned, you have seen the really how it, like the three-dimensional visualization, how it happens. So what is the entropy? The definition of entropy already I have told in my third lecture. So you should answer that what is the entropy. So entropy means change. So it is the change in this property is used to determine the direction of the process will proceed. So we can say it is a randomness of the system that is called entropy. So from the entropy, we can understand that the process is spontaneous or not. It is like reversible or not, how it easily will take place or not. So what is the physical significance of entropy? Physically, entropy is a measure of the disorder of a system. Okay, it is the disorder or randomness of a system. When a gas is heated, so it will increase or decrease. Can you tell? Yes, the Q reversible will be increased. It is a positive. Intermolecular attraction between the gas molecule decreases. They will be more chaotically distributed, or disorder of the system will increase. So we can say the entropy will be increased. As you know that ds is equal to dq reversible by t. Okay, ds is equal to dq reversible by t. So now we will see that how the process is spontaneous or not, how we can understand from the entropy value. So you know that the entropy of the universe, that is represented by del S universe, or you can say del S total. So here it is equal to the entropy change for the surrounding and change of entropy for the system. So change of entropy for the universe, or we can represent it is for the total, is equal to the change of entropy for surrounding and change of entropy for the system. Now, if del S total is positive, or del S, you can write the del S universe is positive. Positive means the greater than 0. The process is spontaneous. Okay, so this process will be spontaneous. If say the del S total is negative, so del S total less than 0, the process is non-spontaneous. Now, the del S total is 0, the process is in equilibrium. So in this way, we can understand that the process is in spontaneous process or non-spontaneous process, or it is in equilibrium. So now we will learn the work function or Helmholtz energy factor. So A is the thermodynamic property of a system such that it gives the maximum work available during isothermal change of a system. So how it can be represented mathematically? It can be represented mathematically that A is equal to U minus Ts. So physical significance of A. So if there is the change in A, so we get del A is equal to del U minus T del S. And you know that del S, the change of entropy, is equal to Q reversible by T. You have learned it. Okay, so we are getting that del A is equal to del U minus Q reversible. Now from the first law of thermodynamics, you know that Q del U minus Q reversible is equal to W reversible. So we can write del A is equal to W reversible is equal to W max. Okay, so del AT is equal to, for the isothermal reversible change, we get minus delta AT is equal to minus W max. So for an isochoric process, that means the volume remain constant throughout the process. That is the isochoric process. So if we take that delta A by delta T and keep the volume constant, we get that is equal to minus S. If we take the isothermal process, so this is the delta A by delta V, and what is the constant? The T, the temperature is constant. Then we get the value that is minus P. Okay, so for any spontaneous process, delta A less than 0. Now, the factor that is the Gibbs free energy. It is very important. It also determines the spontaneous process or non-spontaneous process, spontaneity of a process. In thermodynamics, the Gibbs free energy is a thermodynamic potential that can be used to calculate the maximum of reversible work that may be performed by a thermodynamic system at a constant temperature and pressure. And how we can explain mathematically? So G is equal to H minus Ts. So here we get the expression G is equal to H minus Ts. Okay, if then you know that very well that H means H is the enthalpy. We can write U plus PV instead of H. You have learned in the previous lecture the expression of H. H is equal to the internal energy plus PV. Okay. Now what we are getting, if you take the derivative, dg is equal to du plus pdv minus tds minus sdt. delta PT is equal to, you will get the expression. If we take the constant pressure, constant temperature, then constant pressure, that means dP will be 0 and dt also will become 0. This dt and dP at the constant temperature and pressure. So we get that P dV and the T ds. Okay. So we are getting this term. We are getting this term. So these are being 0. That is why we are getting this term. Now, thus the free energy is the property of a system whose decrease is the measure of external work available during the transformation of the system. Okay, so in this way, Gibbs free energy is a portion of total system energy that is available for useful work. So if we again take the isobaric process, that means the pressure is constant here. We get delta G by delta P at constant pressure. It will be equal to minus S. The constant pressure, that means the pressure term dP will be equal to 0. For the isothermal process, we get delta G by delta P at constant temperature. Isothermal means the temperature is constant, is equal to V. So this form you will practice at home. Okay. So you practice all these things at home to get the conception clear. Now, the free energy of formation, the standard free energy formation is defined as the change in free energy to form the compound from its constituents elements, which are arbitrarily assigned a value of 0. So free energy for reaction also we can calculate. The free energy of reaction is equal to the sum of free energies of formation of the product minus the sum of free energies of the reactants at standard state. Okay, so the mathematical expression also given here. So free energy changes for the products minus free energy changes for the reactant. So in this way we can calculate the Gibbs free energy for reaction. Further, we can relate the free energy of a single substance at a state other than the standard to its free energy of formation at standard state by the expression. So now, what is the criteria of spontaneity? Condition for a reaction to be spontaneous are tendency to achieve minimum energy, and number 2, the tendency to achieve maximum randomness. So we can recall the expression of the Gibbs free energy. So here you can see that del G is equal to, already you have done in this lecture previous pages. So it is del H minus T del S. So del H, that is the energy of enthalpy factor, and T delta S, that is the entropy factor. So first one, the energy factor or enthalpy factor, we need to minimum energy, okay, tendency to achieve minimum energy, and tendency, the randomness, that is the entropy factor, tendency to achieve maximum randomness. So if the value of del H is minimum and T delta S is maximum, so the delta G will be negative or positive. Del H is lower, minimum, and delta S is maximum. So it will be negative or positive. It will be negative. So it is the criteria of spontaneity. Okay, so let's see what are the criteria. Okay, so this is the condition. If delta G less than, these are very important, very important, the criteria for spontaneity. You can explain by the entropy, and also you can explain by the Gibbs free energy. So here, for the Gibbs free energy, it is giving that delta G less than 0, that means reaction or process is spontaneous. Spontaneous in the forward direction. Delta G greater than 0, that means the reaction process is non-spontaneous. So reaction is favored in the opposite direction. If delta G is equal to 0, the system is at equilibrium. There is no net change. So can you recall that what you have done for the delta S? If you know the delta S value, so what is the criteria for the spontaneous reaction? Remember the delta G less than 0. And from here you can see, if like say this factor, it is the entropy factor. Basically, this is the entropy factor. If it increases, then delta G will be decreased. Like say if delta S increases, okay, then delta G will be decreased. That means if delta G is negative, then the entropy delta S will be positive. Delta S positive, that means delta G negative. So the criteria for spontaneity will be just reverse. That means for spontaneity, we require delta G is less than 0, where the delta S must be greater than 0. So we also can check what I have told previous. So here you can see the spontaneity criteria. Okay, it is the criteria for spontaneity. If you can see very well, if the delta is greater than 0, we get spontaneous. Delta is less than non-spontaneous, so it is just the reverse. So delta is greater than 0, that means, so that is tending to the delta G becoming less than 0. So the condition is opposite. Delta is less than 0, that is the spontaneous process, but delta is greater than 0, that is the spontaneous process. Now Gibbs-Helmholtz equation. The Gibbs-Helmholtz equation provides information about the temperature dependence of the Gibbs free energy. So Gibbs free energy dependent on the temperature. The derivation of Gibbs-Helmholtz equation begins with the fundamental equation for the Gibbs free energy. So it starts from the fundamental equation, that is that del G dG is equal to minus SDT plus VdP. So using relation for the exact differential. So if we take the differential dG by dt, we get at constant pressure, at constant dG by dt at constant pressure. So this pressure term will become 0 and we get minus S. Okay, so substituting this result for minus S into the equation defining the Gibbs free energy, G is equal to H minus Ts. So we are writing in this equation. So we are writing, instead of S, we are writing that dG by dt. Now we get this expression. So in now divide both sides equation and leads to the result that G by T is equal to H by T plus D delta G by delta T at constant pressure. So Gibbs-Helmholtz equation involves the partial derivatives with respect to temperature of quality on the left side. So in this way, you derive this term. So you go through this equation and you derive, you write down, you try to write down yourself. Don't see what is given here, okay? Then you try to write down yourself. So using the relationship for the exact differential, we have that delta A by delta T at constant volume is equal to minus S. So A is equal to will be U plus T delta A by delta T. So you take all the equations, all the relationship like the from the first order, what you got, okay, and from the enthalpy equation, and what is the entropy equation. So all these things you write down and you relate with all these things. Then it will be very clear, and any sum you can solve easily. Now Maxwell relations. Maxwell relations are a set of equations in thermodynamics which are derivable from the symmetry of second derivatives and from the definitions of the thermodynamic potentials. These relations are named for the 19th century physical James Clerk Maxwell. So, these are very important equations. These are the derivatives, the important derivatives we can get as Maxwell relations. So, these are called Maxwell relations. So, first one, that is the delta T by delta V. When the S is constant, S means you know that is the entropy. Then we get that is equal to minus delta P by delta S at constant volume. Second, the delta T by delta P at constant S we get is equal to delta V by delta S at constant pressure. The third one, okay, so I'm showing first one, second one, the third one. Delta P by delta T at constant volume is equal to delta S by delta V at constant temperature. The fourth one, delta V by delta T at constant pressure is equal to delta S by delta P at constant temperature. So you try to derive that, you try how it is coming. It is very easy if you know the expression of all these things, that what is the first order expression, what is the entropy expression, what is the like Gibbs free energy, the relation with the other terms, and what is the enthalpy equation, then you can easily do all these things. Now, the numerical problems, we can calculate the entropy of the universe or total entropy. So it is given if 1.6 gram of CH4 reacts with oxygen gas to form water and carbon dioxide, what is the change in entropy for the universe? So here, that is CH4 plus 2O2 will be equal to CO2 plus 2H2O. That is a reaction you know. So first thing we have calculated, we have to calculate the for the system entropy change for the system, that is the entropy change for the products minus entropy for the reaction. So we have put the value and we got for the system. Now enthalpy for the system also we will get if we subtract the entropy of the reactant from the entropy of the product. Sorry, not entropy, enthalpy of the reactant from the enthalpy of the product. Then if we put the value, you will get the values. Next is the S surrounding. S surrounding, S means the change of entropy of the surrounding is equal to change of entropy system by T. So if you put this value, you will get the result. So now you got for the surrounding and you have got for the system. Now the total entropy, if you summarize these two, then you will get the total entropy or the entropy change for the universe. So I hope that you have understood very well what you have learned today. If I summarize, that you have learned the entropy concept. You have seen a wonderful video of the entropy change of the materials. You have learned how the first law and second law is coming, and the second law and the entropy. And you have learned to write the condition for the spontaneity with the value of change of entropy and also with the value of Gibbs free energy. Then you have learned the Maxwell relations. You have learned the Gibbs-Helmholtz equation. Also, you have learned to calculate the entropy for the reaction. Okay, so today I am ending my session. If you have any doubt, you can communicate with me. So thank you everyone.